Let us quickly review the topics that we have seen this term. So the course was all about intractable computational problems, and we can divide the approaches that we have seen into upper bounds and lower bounds. So we have seen upper bounds on the amount of resources that we need to solve or approximate these problems. So those are positive results, our algorithms, where we actually manage to tackle these problems. We have also seen lower bounds that give us some impossibility results. So it's not possible to achieve this or that running time under some complexity theoretic assumptions. And the second part, we will briefly talk a bit about what is currently happening in the research in parameterized algorithms and exact algorithms. Okay, so a very good idea if we tackle some intractable problem is to do some pre-processing. And here we have seen the notion of kernelization, where in polynomial time we produce an equivalent instance whose size is upper bounded by a function of the parameter. And this needs to be an instance of the same problem. So we just pre-process our instance and make it hopefully smaller. And this is something that we can always do, no matter whether afterwards we use a heuristic or an exact algorithm. Pre-processing is always a good idea. And then we jumped up from polynomial time to fixed parameter tractable time. So we allowed our running times to depend super polynomially on some parameter k. And so we got some algorithms that were able to achieve such running times. And of course, so these are only viable if for those instances where the parameter is kind of small. And we saw that, well, typically this function is not huge, except maybe when we saw some very general techniques, such as monadic second order logic. In general, when we design our own algorithms, these functions are kind of manageable. Something I would like to highlight here is that, well, after FPT come these intractability classes. If it were the case that FPT were equal to W1, so if W1 problems could be solved in FPT time, then the exponential time hypothesis would fail, meaning that 3 satisfiability could then be solved in sub-exponential time. So that's why we think that FPT is not equal to W1. And so W1 hard problems do not have FPT algorithms. We have seen branching algorithms, which is a quite convenient technique to obtain these FPT algorithms, where we make sure that when we branch into our subproblems, the parameter somehow decreases. And also the number of branches cannot be too large, so then we get typically these FPT running times. We have also seen more advanced techniques to upper bound the size of the search trees that we obtain in these branching algorithms. So we saw measure and conquer, where we can associate a measure to our instances, which acts kind of like a potential function. And this potential function should decrease in every recursive call. And also, so this is the main constraint that will enable us to upper bound the number of leaves of our search tree. Among other positive results, we saw one particular kind of graph classes, namely graphs with bounded trivids. So graphs for which the trivids is not too large. So we saw trivids and tree decompositions, where we decompose the graph into a hierarchy of separators of the graph. And then we saw that, well, processing our graph starting from the leaves of this tree decomposition towards some root by the dynamic programming, we can get efficient algorithms when the tree width is small, or when we are given a tree decomposition with small widths. And we also saw this very general technique about monadic second order logic, where we can quite quickly determine whether a problem is FPT parameterized by the tree-width of the graph. Another technique that we saw was iterative compression, where the compression step assumes that we are given also a solution of size k plus 1, and we want to find a solution of size k. So we saw several examples of how we can exploit the solution of size k plus 1 that we are given as part of the input. And then typically in this iteration step, we are incrementally, well, we are starting from an empty graph and then adding vertex by vertex, or if we start from an empty hypergraph, we add element by element. And then we maintain a small solution for each of these instances that we build up over time. When we discussed randomized algorithms, we saw three techniques for designing randomized algorithms. So one works well when our solution that we want to find intersects a linear number of edges, so a constant fraction of the edges. And then we saw that, well, randomly selecting an endpoint of a random edge and adding this to our solution gives us quite good success probability. We also saw color coding, where we assign a random coloring to elements, such as the vertices of a graph. And then if we want to find a vertex subset of size k, and we use k colors for this random coloring, then we can now search for a colorful vertex set. So a vertex set where every two vertices in the set have a different color. So we saw that, well, the probability that our solution that we have in mind actually is colorful is not too bad. I think this should be e to the power minus k. And then we also saw monotone local search, where we saw that, well, if we have, for subset problems, if we have a single exponential FPT algorithm that finds a solution of size k, then we can turn this into a randomized algorithm that finds an optimal solution, no matter what the size of the solution is, in time 2 minus 1 on c to the power n. And as usual, we ignore polynomial factors using the big O star notation. Then finally, we saw, if we don't look for exact solutions, we saw several techniques. So one is approximation algorithms. Those are, of course, polynomial time algorithms that return a feasible solution, and we get a guarantee on the quality of the solution that the algorithm returns. For example, if we have a two approximation algorithm, then let's say for a minimization problem, we are guaranteed that the solution that we get is at most twice as large as the optimal solution. We saw some heuristics that always return a feasible solution. Those are typically very simple and fast algorithms, but typically we don't get a guarantee on the quality of the solution that they return. We have seen local search, where, well, if we get such a solution from a heuristic or an approximation algorithm, we can always try whether by modifying it slightly, we can improve this solution. And so in general terms, we would then, by repeatedly doing this local search, we would then end up in at least a local optimum in our search space. Okay, so then we also saw lower bounds, typically via reductions. The first one here is not a lower bound, but I kept it because just to emphasize that we can view kernels as reductions. And of course, reductions are also algorithms. So for kernels, the kernelization is a polynomial time reduction Well, that takes an instance to an instance of the same problem. So here we have the special feature that, well, the input problem is the same as the output problem. In addition, we want that the size of the resulting instance is upper bounded by a function of the parameter. Also, the output parameter should also be upper bounded by a function of the input parameter. So, and kernelization algorithms are used to design kernels. I should have also put our polynomial time reductions that we use for NP hardness. And those are just polynomial time reductions that are used for NP hardness with no particular special features. We saw parameterized reductions. Here now we are allowed to use FPT time. So our parameterized reduction is an algorithm that runs in FPT time, where we need that the output parameter is upper bounded by a function of the input parameter. We also saw polynomial parameter transformations, although we didn't call them that. So what are those? So those are just polynomial time reductions with the additional constraint that so the parameter of the output instance is at most polynomial in the input parameter. So we mainly used it with an additional strengthening, namely that the output parameter should be at most linear in the input parameter. So we used those when we talked about the exponential time hypothesis and the strong exponential time hypothesis. They also find uses in kernel lower bounds. So when you have a problem where you know that this problem does not have a polynomial size kernel, then you can also use these polynomial parameter transformations to then show that other problems do not have polynomial kernels either. For exponential time hypothesis lower bounds, we also saw these sub-exponential reduction families that are allowed to take sub-exponential time, but the parameter should be linear. And as a special feature, we have the fact that we can actually use Turing reductions instead of just our standard reductions that result in just one output instance. So here we can use these oracle calls. So this course has prepared you well to solve intractable computational problems in both theory and practice. It has also prepared you to do research in these areas. Let me just briefly mention what research is currently going on. So first of all, there's this influential textbook by Downey and Fellows. And so in this textbook, you can find a list of open problems. And 3 of those have been solved. So the biclique problem was shown in W1 hard. What is the biclique problem? Well, let me tell you what a complete bipartite graph is. For example, K33. It has 3 vertices. It has 2 independent sets of 3 vertices each, and then all edges in between. So the biclique problem is, given a graph G and an integer k, does the graph have a kkk as a subgraph? It's important to note that the kkk should be a subgraph, and it doesn't have to be an induced subgraph. Induced biclique is actually also W1 hard, but that's much easier to show. So Lin needed some quite advanced number theoretic arguments in his reduction to show that biclique is W1 hard. So the next problem that was solved is short generalized text. So it was shown that this problem is W1 complete, and that was shown by a set of authors that it includes several people from UNSW. The next problem that was solved is determining the winner of a parity game, and this problem was shown to be FPT in the number of values. So this is a problem that occurs quite often in verification. So what are the other topics that people are focusing on? So there's a lot of focus on enumeration algorithms and combinatorial bounds. So we saw, for example, that we can enumerate all maximal independent sets in time O star of 3 to the power n divided by 3. And this then also gives us a combinatorial upper bound on the number of maximal independent sets, which is quite satisfactory because, well, this combinatorial upper bound is independent of any algorithm. So we directly tackle the problem and we say something about how many such objects there are. Randomized algorithms have turned out to be very powerful and often lead to faster algorithms. Whereas previously people just designed deterministic algorithms, now people have discovered that randomized algorithms often give a big benefit. Trewitz is still used a lot. So there's new algorithms that compute the Trewitz and tree decompositions, or that give approximations on the Trewitz or constant factor approximations in single exponential time in the Trewitz. People are upper bounding the Trewitz of some graph classes, and this also plays very much into bidimensionality. So in bidimensionality, we tackle problems on generalizations of planar graphs. And what works very often is that either we can use a simplification rule, or if we can't, then the problem or the instance has small Trewitz. And so we can use a win-win. Either we can use a simplification rule or we can use the Trewitz-based algorithms. People have been looking a lot at like turbocharging heuristics and basically been looking at what do people do in practice, how do people actually solve these intractable problems, and then took these approaches and tried to improve them or explain why they work well. The exponential time hypothesis and the strong exponential time hypothesis are very widely used now, even for polynomial time upper bounds. So at the start of the strong exponential time hypothesis, it was quite unclear whether this would be accepted by the community because it's quite a strong conjecture. FPT approximation algorithms are also used a lot now, and also moderately exponential approximation algorithms. So we have approximation algorithms that run in exponential time. So you might think, well, that's the worst of both worlds. So we don't get polynomial time computation and we don't get exact solution. But there's a trade-off, of course. So you might get better approximation factors with slightly moderately exponential running time. Since in practice, what often happens is that so we take our problems, we translate them into some general purpose language, and then use a solver for these languages. For example, there are set solvers that are quite efficient. So when we have a graph problem where we don't have a dedicated implementation of an algorithm, we sometimes translate it into satisfiability and then use an existing set solver that has been highly optimized and returns a solution fast. And there's others such as constraint satisfaction, integer linear programming, integer quadratic programming, etc. So, and since these modeling problems are used a lot in practice, people have now started to investigate these problems much more from a parameterized and theoretical viewpoint. Talking about set solvers, backdoors is of course a very convenient way to try and explain the good performance of set solvers and also CSP solvers and other kinds of solvers in practice. So finally, the parameterized complexity community has branched out into many sub-areas of computer science, such as artificial intelligence, computational social choice, computational biology, and then some people are looking at problems in those areas and try and solve them with parameterized algorithms. And this also leads to improvements in practice, typically. Okay, let me mention some of the resources that might be quite useful. So there's the FPT wiki, there's the FPT newsletter that you can also find on the wiki. There's a general question answer site about theoretical computer science in general, but it contains lots of questions for solving these intractable problems. There have been several summer schools on these topics, and those also contain very nice lecture slides. And there's even more lectures on the wiki here. And something that's quite regular now, so it happens every year, is the Parameterized Algorithms and Computational Experiments Challenge, where every year like a new challenge is presented to the community, and then people go and implement algorithms for some problems. So for example, the feedback vertex set problem has been one of the problems in the past, or the Triwitz problem has been another one of the problems. We actually participated in the Triwitz challenge and implemented our turbocharging of this heuristic for the Triwitz problem. Okay, and these are the references, and that's it for this course.